So here we're looking at direction fields, and there's a code right here, Python code that will do a direction field. So let's see it in action. So we'll go here to a Sage cell, and then I'll go back here and I'll click on this link. It just gives me this code. Everything's really small. Let me make it a bit bigger so you can see it there, and I'll make this a bit bigger. Alrighty. Okay, so here I just highlight all of this. Looks very hard to read right now. But I'll do a Control-C for copy, come in here and do a Control-V for paste. Now it's got some different colors and so forth. So you don't need to know lots and lots going on here, but if you want to try to use it to see some things, yeah, you'll need to know a little bit. So this is Python code, and these first two lines are to bring in packages to help us do things. Then anything with this pound sign or a hashtag in front of it is a comment and is not used. It's just for you to read. And so here what we see are t and x is the way this happened to be made, and I just kept it that way. So t is our independent variable, x is our function variable. And right now what this is doing is making a grid. It's got a lower limit of 0 for t, upper limit of 10, and a step size of 1. So this would go 0, 1, 2, 3 up to 10. Similarly from minus 60 to minus 40 by 2s. And then this takes those two sets of values and makes a grid, okay, much like I did in the previous video. Then, okay, here is the differential equation, and notice it's the x of t, and so it's the x first, then the t is the way it's written here. And in this case, it's just minus 9.8 minus x over 5. Okay, so we'll soon see in another video this is an autonomous equation. But nonetheless, it's just, we'll look at the one that we did in the previous video as well. We'll try that. Okay, so so this is just where you would define your differential equation, and it's just the right hand side. So and so then we've got dx dt here is f of x of t. So in other words, our differential equation dx dt is that right hand side that we'll return here. Then this is a little bit of work to actually create the direction field. What it's doing is, if you study it enough, you'll see that what the U is trying to get at is the x, or sorry, the t length, and the v is trying to get at the x length, and to create the little short lines. Okay, so that's what this is supposed to be doing. Now I also have in here to numerically solve the differential equation, and we'll again try that with the case from the previous video, from the example in the book. But this has an initial value of minus 45. It also needs, this is doing it numerically, so it also needs t-values. In this case, notice it goes from 0 to 10, again a lower limit and upper limit, but now it's not the spacing that goes in there, it's how many of these we're going to use, and this says 100. Now, actually, maybe to be a little cleaner, you might want it to be 101 or something like that. But anyway, here's 100, and so notice it goes from 0 to 10, just like this went from 0 to 10, the t. I would suggest you just have them both match in their lower and upper limits, and then here pick quite a few, probably around 100 to get a good looking solution. And then to actually compute the differential equation values numerically, there's this ODE-int routine. We give it F, which was the name we gave back here where we defined the right-hand side. So we just said F. We gave it the initial value, and we gave it the t values that we're going to build numerically on. So that's all we really need to know to make this happen at that point. And then here, this is all the plotting, and you can probably figure out some things. Title, we got the direction field for this differential equation. They've changed the v's to the x's to v's here. They've labeled the x-axis as time in seconds, the y-axis is velocity. Here, something you could change would be the color, I guess. There are other things you could change. I've attached a document where I got some of this stuff, so if you wanted to play with it more. And here again, here's color, the line size, and this particular plot is of n there. That was the actual differential equation solution, and this quiver part is where the direction field will be made. So if I hit evaluate and wait for a moment, there we go. So there are all the little directions, and there is the solution. And as you can see, it's not perfect trying to use the slopes to kind of connect the dots to make your solution. But you see, if you had said, well, I think a solution that would start around -45 would kind of go like this, and maybe it looks like reach an asymptote, a horizontal asymptote here at, I don't know, -48, -49, somewhere in there, you would be correct. Okay, so we can see that. If we had started anywhere down here with an initial value, the solution would have come up and increased, but again to this, what looks like a horizontal asymptote. All right, so that is the code, and that's that video. I'll make another video where I try to change this up to what we had in the example. So there we go.